the diagram by using the simulator. First, we will construct our circuit by selecting a voltmeter, as you can see on the right, and the ammeter. On the left side, you can see several items for the connection of our circuit. Switch, battery, resistors, and several wires can be used by dragging and connecting them into place with the voltmeter and the ammeter. After which, we can identify the resistance by clicking the color-coded resistor and dragging it to our desired value in an increasing manner. We can also identify the current by looking at the ammeter and the voltage by looking at the voltmeter.
For our procedure, we will be using PhET Simulator as the circuit construction kit DC lab activity. The following data gathered were composed of 5 trials of measurements of voltage, current, and resistance. For the interface of our lab experiment, we have to set up the wires attached to the ammeter, battery, and resistor, as well as the switch. Next, we attach the probe of the voltmeter to end of the resistor, eventually measuring the voltage. The ammeter will measure the current value in ampere. Now for the value of our voltage, we settled to remain constant of 100 volts. For our resistor, we set 5 values in an increasing manner, and we determined the theoretical current through computation using Ohm's formula, after which all the data was subjected to discussion, observation, and analysis.
For the table, there are 5 trials which consist of the resistance, experimental voltage, experimental current, theoretical voltage, and theoretical current. For trial number 1, the resistance is 10 ohms. The experimental voltage is 100 volts. The experimental current is 10 ampere. The theoretical voltage is 100 volts. The theoretical current is 10 ampere. For trial number 2, the resistance is 20 ohms. The experimental voltage is 100 volts. The experimental current is 5 ampere. The theoretical voltage is 100 volts. The theoretical current is 5 ampere. For trial number 3, the resistance is 40 ohms. The experimental voltage is 100 volts. The experimental current is 2.5 ampere. The theoretical voltage is 100 volts. The theoretical current is 2.5 ampere. Trial number 4, the resistance is 50 ohms. The experimental voltage is 100 volts. The experimental current is 2 ampere. The theoretical voltage is 100 volts. The theoretical current is 2 ampere. For trial number 5, the resistance is 80 ohms. The experimental voltage is 100 volts. The experimental current is 1.25 ampere. The theoretical voltage is 100 volts. And the theoretical current is 1.25 ampere.
For the computations, the formula for finding the theoretical voltage is the current multiplied to the resistance, and the formula for finding the theoretical current is voltage divided by resistance. The experimental voltage was constant at 100 volts for all 5 trials. For trial 1, the resistance was at 10 ohms and the current was 10 amperes. These 2 values were multiplied to get the theoretical voltage, which is 100 volts. For the theoretical current, 100 volts was divided by the resistance with a value of 10 ohms, thus getting a value of 10 amperes. The same process was done for trials 2 to 5. The theoretical voltage is the same for all 5 trials at 100 volts. However, the theoretical current for the succeeding trials are the following: 5 amperes for trial 2, 2.5 amperes for trial 3, 2 amperes for trial 4, and 1.25 amperes for trial 5.
Discussion. Ohm's law states that the current flowing in a circuit is directly proportional to the applied potential difference and inversely proportional to the resistance in the circuit. In other words, by doubling the voltage across a circuit, the current will also double. The law was named after the German physicist George Ohm in 1827. Described measurements of applied voltage and current through simple electrical circuits containing various lengths of wire. It has a mathematical equation I is equals to V over R, where I is the current through the conductor in units of ampere. V is the voltage measured across the conductor in unit of volts, and R is the resistance of the conductor in unit of ohms.
One of the major observations regards the relation of resistance to current, both as electron flow and conventional current. The electrons flow from the negative side of the source to the positive side, unlike conventional current, which flows from the positive side to the negative side. Correlating the resistance value from the resistor, when the resistance is high, the current of the electrons slows down and speeds up when the resistance is low. Same is seen within the conventional current. The higher the resistance, the slower the current, and the lower the resistance, the faster the current. Another thing that can be seen, when the voltage is high and the resistance is low, both the battery and the resistor cannot withstand the current, thus it can be seen that both are broken and are on fire. Comparing the results in the table, the resistance which is set in an increasing value has resulted in an experimental current which is decreasing in value. The same exact relationship is examined in the theoretical current compared to the given trial of resistance. The voltage in both experimental and theoretical is seen to be constant in both settings, while the experimental and theoretical current show the same values for their respective trials. Thus, both the experimental results and theoretical results have proven that the current has an inverse relationship to resistance even if voltage is held constant.
And for our conclusion, the resistance which is set in an increasing value has resulted in an experiment current which is decreasing in value. The exact scenario is seen in the solved theoretical current. The relationship still exists even if the voltage in both experimental and theoretical is set constant. Therefore, in conclusion, both the experimental results and theoretical results have proven that the current is inversely proportional to resistance even if voltage is held constant, thus verifying the Ohm's law to be true and correct.